Good morning to all my friends. This is Physics STPM. Welcome to join Physics STPM. I'm Mr. Koo. Topic 3, Dynamic. In topic 2, we study about different type of motion. Right? Basically, this graph shows you the summarize for you. Some of the motion, right? Uniform acceleration, this acceleration time graph, this velocity time graph, uniform acceleration, or if it's a displacement time graph, it is a parabola. Right? We will be using a lot of this mass, right? Where area under the graph from A to B is the function, right? The function or the graph, this graph times your dx, that's your x, right? Or sometimes people call it y. Right? This is the book that I use, which I'll introduce to you in a while. Topic 3, we study. Topic 2, we study about kinematics, motion. We didn't give you the reason why they are moving. Topic 3, we give you what causes acceleration and how to calculate the force. Right? Important to, when you study physics, STPM, you must have the syllabus with you. Syllabus tell you how wide you have to know, what to cover. Right? So we will be covering this topic today, Newton's law of motion, state Newton's law of motion, and then know how to use this equation. Then later topic we'll go into that. So syllabus is important. Right? These are other areas we'll cover later on. So these are unofficial textbook. It can be used. Of course, you must always remember it's not perfect. There are mistakes there. Right? Occasionally there may be some mistakes there. You may want to consider using either of this one where they are partial paper. But I'm using this one. Right? Most of my page number is from here. And I'm using this one. This is also old partial question paper. If you want, you have to get it updated. So you have to have an unofficial textbook. Unofficial means not recognized. So you have to be careful about the definition is follow standard textbook. Right? Sometimes they may make mistake there. Right? So this is your partial paper you must have. Right? After practicing here, then do the partial paper. These are some of the reference textbook from the syllabus. Right? This is the oldest one. I used it when I was in the 70s. Right? Of course, this is a new edition, the 7th edition. You can try the others, but as I say, textbook is a bit wordy. A lot of things are not in the syllabus. A lot of things in the syllabus are not inside there. So that's the weakness of textbook, because the syllabus give a lot of American books also. Okay, let's just summarize for you Newton's law of motion. Then after that, 3.2 is linear momentum and its conservation. 3.3 is elastic and inelastic cohesion. That's our next topic after this one. And center of mass. 3.4, 3.5 frictional forces. Okay, let's go to dynamic. That's the page there. As I said, I'm using this book. Right? Same author. I said this one doesn't have partial paper, but it's a reasonable book to use. You must have a book so that you can practice the question and know how to use the formula. Because there's so many formulas. One way to memorize formula is to keep on using it. They become part of you. Just to summarize for you, you study about Newton's law. And after that, we go to linear motion, linear momentum and its conservation. So we will state, and then after that application, that's mainly your SPM work, mass and weights. momentum, we define the Newton momentum. That's our momentum. Right? There's a change in momentum. Define momentum. Right? So that is how we define momentum. That is the formula. And under that linear momentum and its conservation, we will state the principle. Then we look at collision. And we look at elastic and inelastic collision. I can draw your mind map. Right? Different people, this is my own mind map. I can add more information for me to remember. Now you can draw your own mind map. This can be obtained from the internet. Okay. Okay, let's go to 3.1, momentum, the Newton's law of motion. That one this Newton's law, you must remember. Memorize an object at rest. Right? If it's not moving, it will remain at rest. An object in motion continues in motion with the same speed in the same direction. That means the velocity is constant, unless there's a condition acted upon by an unbalanced force. Right? Unbalanced force is the resultant force. Yeah, there can be many forces acting on it, but we are looking for one resultant force. Right? So the object we say has inertia. What is inertia? Tendency of the object of an object to stay in a state of rest or uniform motion. If it's not moving, it doesn't want to move. If it's moving, it continues with its own more uniform motion. So we measure this inertia by mass, which is defined as the property of a body which receives change in motion. Greater mass, it receives greater resistance, greater resistance to motion. So that's why we define a property of body which receives change in motion. In lower form, you measure. Easier for you to understand is a measure of the quantity of matter. Mass is a measure of quantity of matter. Right? So application of the first law in daily life. Right? This person is in the train. The train is moving to the left. That's the train is moving to the left. So the leg is following the train. The body is stationary. So that's why the body remains stationary where the train is moving forward. So that's why you have to hold. If you don't hold, you fall down. Right? If you accelerate too fast. Okay, mass. Defined as a property of a body that receives its motion. A measure of the quantity of matter. Scalar quantity. It doesn't have a direction. Measures the inertia of a body. It's a constant in any gravitational field. If the gravitational field is uniform, then it's constant anywhere. Unit is kilogram. Okay, so let us restate Newton's first law again. Review it. That football there, object, it's not moving, it's stationary, so it remains stationary. Right? So at rest, remains at rest, in motion, remains in motion. So if you kick it, right, that's a condition. Unless tell you the condition, no balance force. No force on it, it remains at rest. But when you kick it, you are giving it an impulse or force. Right? It will move. Right? If you forget about gravity, it will be in a straight line. That's Newton's first law. Moving constant uniform velocity in a straight line. Unless it hits a net or fence that will restrain it from moving further, then we'll stop it. Right? That's a condition. Unbalanced force. That net is the unbalanced force. Stop it. So we can summarize Newton's first law. Unbalanced force, that means no resultant force. Object at rest, not moving. And then another case, object is moving. Right? Remember, an object must have a mass. So unbalanced force, we call it 0. So in this case, resultant force is 0. Or we can say sum of forces equals to 0. Or that's the best way of writing it. Sum of forces, remember, it's a vector quantity. So whenever you want to do maths, you must see it as a vector. It's a force is a vector quantity. Object at rest or moving with uniform velocity. Object at rest, object moving uniform velocity. Right? So if at rest, it remains at rest. The final velocity is 0. The final velocity is still constant, same as initial velocity. Right? And summarized by this diagram, it will stay at rest. If it's at rest, stay at rest. Right? No acceleration, no force. Right? No resultant force, no acceleration. So it remains in motion. That means same speed and direction. Or you say uniform velocity. Right? Unbalanced force is a resultant force, or some people will call it a net force. Different term used as well. Newton's second law of motion. Right. Let me just review a bit of my short form. First law of motion, I call it Newton's first law of motion. Right? Newton and F, first law, L, law, O, M. That's my short form, right? Rather than every time writing all this long thing there. So that's Newton's first law of motion. Then same thing, that's my short form for second law. Newton's second law, L, of motion. Right? Rather than always state that Newton's second law of motion, I use NS, LOM. Okay, you must remember, rate of change in momentum is proportional to the applied force, and the momentum change takes place in the direction of force. That means the momentum and the force are in the same direction. Change in momentum. It gives us a method of finding the magnitude of the resultant force. Then we look at collision. In a collision, the amount of damage depends on mass, on two things. Mass of both cars and the velocity. Not on mass alone, not on velocity alone. Like a fly, not on a car, would not cause much damage. Right? Because the mass is small. The velocity is also small. The bullet can shatter a windscreen because of its velocity. Velocity is large, the mass is small. So that's why we have to define another quantity, new quantity, momentum. Right? So that is the object of the ball, football. It has a mass m. With moving velocity v. So we define a new term, definition, memorize it, mass times velocity. Usually you prefer to write in mathematical form. Right? Can write as a vector, or it's understood. You must know that it is a vector. Velocity is a vector, momentum is a vector, mass is a scalar. Right? So if one can show a vector curly sign there to show it's a vector, but it doesn't matter. Doesn't need to. Usually textbook will use dark letter called boldface. Mass is in kilogram, velocity is meter per second. So the unit is kilogram, meter per second, or Newton second. Right? Yeah, from there. Momentum, mass is kilogram, velocity is meter per second. It's a vector quantity. Right? Mass is a scalar, this is a vector, velocity is a vector, this is a vector. So the direction of momentum is the same direction as velocity. Momentum is the same direction as the velocity. Right? So the velocity determines the direction of momentum. Then we define another term, change in momentum. That's a body as a mass m, moving with a velocity u, initial velocity u, after a certain time. Right? It moves with a velocity, final velocity v, mass hasn't changed, right? Because it's a force is acting on it. So there's a change in momentum. So we define change in momentum as final momentum minus initial momentum. So we can rewrite as change in momentum equals to final momentum, right? F for final, I for initial momentum. And remember, this is a vector, this is also a vector, so this is also a vector, right? A resultant is a resultant momentum or change in momentum. Or we can write that as change in momentum, final, mass times velocity. Initially, mass times velocity. Take the mass out. Okay, let's now calculate force from Newton's second law. Right? Force, remember the force is the resultant force. Right? That's why it's given there. Usually it's in this form. When it's become rate, it's this form. If it's constant force, then we use this equation. Usually it's a differential equation. Delta T is a small change in time. Time for the change in momentum. Right? Or sometimes we prefer with a small change in momentum, a small change in time. Right? Newton's second law can also be written as that. Right? This is acceleration. Right? So in this case, if both mass and velocity are changing, for constant mass, this is 0. Right? Constant mass is 0. You get that? Constant velocity or uniform velocity, this is 0. So we got that only. Right? So in a particular equation, you have to see whether both are moving, both are changing, then we use this equation. With constant mass, we just that mass times acceleration, or we differentiate. Basically, we differentiate dm dt, that's all. Force is defined as the rate of change in momentum. Force can be visualized, help us to understand what is force. I have to think of force. It's a push or pull. Force is defined as the rate of change in momentum. Right? That's how we define. Newton's second law help us to define force. That's the equation. And remember, it's a resultant force. We can take delta T across there, and we define a new term, impulse. Impulse is just a force times the time that the force is applied. Or from this equation, we say is equals to change in momentum. The impulse causes a change in momentum. Or the force acting at a certain time, force times time, change the momentum. So if it's a varying force, normally we use integration. Use the dt across there. Integrate that, impulse. You need same as momentum. Same as momentum. Right? Force is kilogram meter s minus 2 per Newton. Unit of impulse is the same. Right? Unit of impulse is same as momentum. It's force times time. Right? Force is mass. Same as momentum. Right? Or you can show it from here. Newton second is actually kilogram meter per second. Okay, deriving the equation F equals ma. Right? F equals ma is a derived equation. Definition is from Newton's second law. Right? So suppose a force acting on a body of mass m and changes the velocity from u to v. I can draw a picture of it. There's a body. There's a mass m. Initial velocity is u. And there's a force acting on it at time t1. And at time t2, the velocity is v, and the force is still acting on it. So that's Newton's second law. It's the equation. So replacing the change in momentum, we are using this one, change in momentum. Right? That's what we get. Change in momentum, final minus initial divided by the time of change. That's the time of change. And that one is acceleration. P minus U over T is acceleration. So we get F equals ma. And the change, the small change in time T2 minus T1. Right? Or sometimes we call this 0. And call this T. Right? So it's be flexible to see the context where the examiner or the question give you. So when the force is in the same direction as the velocity, the momentum increases. Right? Or we say the body accelerates. Right? If the body accelerates, it changes velocity initially, increase to final velocity. Right? And then we just times mass, that's all. To the velocity, we get momentum. So if there's a force acting, same direction as the velocity, the momentum increases. Definition of Newton. 1 Newton is a force which acting on the mass of 1 kilogram produce an acceleration of 1 meter per second. Okay, this is an object acted by a force. This one you study under motion. You should be able to read the graph. This is the initial velocity. This is the final velocity. This is the time capital T. Right? Where it has an acceleration. After that is uniform velocity. So from time 0 to T, equal to T is uniform acceleration. Right? That's why acceleration is a gradient. Right? This is X, this is Y, this is a y-intercept. Okay, so you should be able to read this graph. Or should be able to interpret that this is a V minus U is your change in velocity. Okay? So uniform acceleration. So to calculate the acceleration, you just get your change in velocity divided by that time there. Right? Replace this T with that capital T. Because the gradient. I can read it from this graph there. Right? This is velocity, this is U. So the gradient is this part there. Is your acceleration. And then should be able to also draw the acceleration time graph for this graph. This uniform acceleration, right? Constant acceleration, no acceleration, zero acceleration. Then should be able to interpret what's the area under the graph. Okay? Go back to the equation, that's all. Same thing as before. Acceleration is this one. You take that one across there. That's your AT graph. Right? So the area under the graph is a change in velocity or acceleration time graph. Right? No different. We are still using the same graph as this one and this one. I just multiply m here, multiply by m here. That's all. So I got initial momentum, final momentum. So you should basically say momentum is increasing and uniform momentum. Right? Previously we used velocity, now we use momentum. Same. Right? So change in momentum equals to Ft, same as a velocity, change velocity is A times T. Right? Or we can rewrite the change in momentum is the P, final momentum, minus initial momentum to the other side, you got that? Right? And there's your Ft there. Right? Or compare with this one, you can multiply this by M, this by M, this by M. This becomes your momentum at any time. This becomes your initial momentum, one. And MA is your F. Okay? So you should be able to say, okay, this gradient is force. Previously, velocity time graph is acceleration. So now momentum time graph becomes force. Gradient becomes a force. Right? So gradient of the graph is the force. How to calculate the force. Then force time graph. Right? Force time graph, you just take this across there, Ft. This is your F, this is your T. So it becomes change in momentum. Or we can rewrite calculus from dp equals to 0 to T F dt. So that area is a change in momentum for force time graph. Right? Let's introduce our terms to calculate weight. Right? That's our derived form of Newton's second law. Weight is the effect of gravitational field on a mass. When the mass is placed in the Earth's gravitational field, it experiences a weight or force of gravity. It means it experiences acceleration. No? So Newton's second law, in this equation there, replace that with W, M still the same, A with acceleration due to gravity. Right? And that G varies from place to place. North Pole and equator, slight differences. And G is called the acceleration due to gravity or gravitational field strength. Right? So it's the effect of gravitational field on the mass. It's the force of gravity on the mass. It's a vector quantity. Whenever we come to force, it's a vector quantity. Vary from place to place, depends on the gravitational field strength in the place. Right? Gravitational field strength or acceleration due to gravity, same thing. Right? Application, resultant force, we have a car. Right? The engine provide this thrust to accelerate the car. Then, as the car is moving, right, air opposes the body, and there is also force resistance between the tire and the ground. So we have what I call drag. Opposing, it always opposes the thrust is the determine the motion, direction of motion. That always oppose the thrust. Opposing the force due to air resistance and friction of the road on the tires. Okay. Okay. Four tires, not one tire only. When the thrust is greater, this one is greater than drag, then we use Newton's second law or derived form to calculate the resultant acceleration. Right? T minus D will give you a resultant force, and that's your mass of the car times your acceleration of the car. So the acceleration is in the direction of the thrust. The car may be moving from rest. As the thrust increases, the velocity increases. Right? Initially, may not be moving, it may be at rest. Start the engine, it starts to accelerate. But when it starts to accelerate, the drag comes increase with velocity. Right? Drag is the resistive force that increases velocity. As velocity increases, this will increase. When the thrust is balanced, it cannot exceed. When the thrust is balanced by the drag, the car moves with uniform velocity. Right? So this can only increase until the two are the same. Then the car will continue with uniform velocity. The car cannot move any faster anymore. Right? So we call that equilibrium. T equals to D. This is where the acceleration is zero. And the velocity, we give it a special name. Constant maximum velocity, we call it terminal velocity. Right? Can summarize what happened when the force is acting on a car at zero. right? Net force is 0. Two things can happen. Stationary car, right? Stationary car has mass. Force is 0. So V equals to 0. So it means the final velocity equals initial velocity if there's no force acting. So the car remains stationary. Or car, right? Car has a mass. It's moving velocity u, force is 0, right? So that multiplied by 0 is still 0. So we got your V equals to u. That means the final velocity equals initial velocity. The car continues with uniform velocity. And we can recognize that, right? This is a special case of second law, but this is Newton's first law of motion. So Newton's first law of motion is a special case of Newton's second law of motion. And that means they are not independent laws. The first law is a special case of second law. We don't have first law, we can derive from second law. The laws are not independent. That's why we say the laws are not independent laws. First law can be obtained from the second law. Then let's look at other example that you have encountered in your projectile motion. Right? There's your cannon. There's cannonball. If there's no gravity, you shoot a cannon. Cannon will move with uniform velocity in a straight line. But because there's a resultant force acting on it, called the weight, right? If we throw another ball horizontally, it will move in a parabolic path. So in this case, the force of gravity, which we call the weight, is the resultant force. Wherever it is, the force is acting on it, pulling it down. So condition for this parabolic path would be force is constant. This is the force acting, the resultant force acting is constant and always in the same direction. Doesn't change, the force doesn't change, always in the same direction. The cannonball is moving at an angle, right? Not vertically, not thrown vertically. It can be shooting upwards, it can be shooting downwards there. As long as it's moving at an angle, it's a parabolic path. Okay, so in this case, where it's being pulled downwards, that's the resultant force, which is the weight. Right? Other application, right? You wear seatbelt, airbag plus three-point belt in a car is for safety. When the car collides with another car, the inertia of the driver causes him to continue to move forward. Right? The car may brake, but the body is still moving. Right? The body has the inertia or a mass, so it will keep on moving forward. So that's why you need a seatbelt to restrain the person. Seatbelt restrain the passenger from continue to move forward when the car brakes suddenly. Right? Another added safety, seatbelt. Airbag. Purpose of airbag, increase the time of impact. And we are just using this physics, Newton's second law. Right? You increase this time, this force becomes smaller. Right? What's the force? The steering wheel is going to provide a force acting on your chest. At the same time, when the bag is bigger, right? You spread the force over a bigger area. So the force per unit area is smaller, or we call that pressure. Right? So you can draw your mind map to summarize all the formulas that you have learned. Right? Newton's second law, Newton's third law. Newton's third law of motion. Newton's third law of motion. For every action, there's an equal and opposite reaction. Right? This one sitting on a trolley. Reason trolley is less friction. So when I throw a ball forward, that's the action. Then there's a reaction, he's been pushed forward. That's what we do in outer space there. There's no friction there. So you want to move backward, you throw something forward. So Newton's third law of motion, that's my short form. An alternative way of saying is a push or pull of a body A on body B is always equal but opposite to the push or pull of B on A. Right? Here's your body A. This is your body B. This is an example. Right? Positively charged. So in this case, body A, right, push on body B. Body B push with a repulsive force on body A. That's why it's repelling each other. Right? These are action and reaction forces. Right? You can call either one, whichever one is action, which is reaction, doesn't matter. If this one started first, this is action, push on this one will push it back. Right? So in this case, the force of B on A equals to, we put a negative sign, force of A upon B. Right? This is the same, the Earth and the Moon. Right? Always occur in pair. The two of them are equal by an opposite direction. They are equal, but they are in opposite direction. This one act on the Moon, this one act on the Earth. Right? This is a short form for force of Earth on Moon. This one acts on the Moon. This is a force of Moon on Earth acts on the Earth. Right? This is a gravitational force. We will study, I think, topic 6. Both, in this case, both are the same nature. That means both are electric force. Same origin. Two bodies are not necessarily in equilibrium. Right? In this case, there's a resultant force. Right? When they are close together, they will repel. Repel to a certain distance, then they will stop. Right? Because the tension will be the one stopping it. Right? Remember, it's not equilibrium. There's a resultant force. Not necessarily to be in equilibrium. Right? Other example, shoe pushing on ground, ground pushing on the shoe. Same, earth pulling on man downwards. This earth pulling on man downwards. And then the man pull on the earth with the force of gravity upwards. Right? There's a pull of the man on the earth. Right? That's a common mistake. Right? Which you do in the STPM. Force of gravity pull on the book due to the earth. That one is because of the earth is pulling it down, not the table. Reaction force is the table pushing on the book. Usually we teach you that's the reaction force pushing on the book. But this is wrong because the reaction force of the table on the book is negligible. The reaction force is a book pulling on the earth. That's the earth there. Must imagine that that's the earth there. Right? This is the earth pulling on the book. The book is pulling on the earth. That one should be acting on here. That one there. Right? Pull of the book on the earth. That's the reaction force. Without the earth, there's no weight. Yeah? There's no weight, this one. The acceleration of the table on the book is very small. Right? So that reaction force is not from the table, that reaction force is because of the earth. Right? Other example. Right? Balloon that is filled with air is released. The air pushes down. Right? The balloon will move upwards. That's the reaction. Or you fire a gun. Right? It will require. That's the bullet go forward. Require the other way. Right? Let's finish off with solving some problem. Accelerating car. Right? There's a thrust provided by the engine. There's a drag, opposing force due to air resistance and friction of the road and the tires. When the thrust is greater than the drag, the car accelerates. Right? That's how we calculate previously. When the thrust is balanced by the drag, the car moves with uniform velocity. That's what we summarize for you. previously. Braking a car. Right? Braking a car, resultant force not zero. Remember that it's moving at constant speed, then you apply the brake. Right? Direction of motion. Direction of friction is opposing the motion. Right? Friction opposes motion. Braking a car slows to a stop. Right? Friction is called the unbalanced force in this case. It decelerates the car to a stop. Sometimes we use the term smooth surface. Smooth surface means there is no friction. For instance, on ice, the car continues to move with constant speed. Right? Rough surface means there is friction. Right? Remember your maths, you'll be using area of this trapezium. You add these two, divide by half, and times the height. Okay, what does the area under the force time graph represents? Well, you want to try it out. Stop the video, try it out, and check the answer. The graph shows the force acting on a body varies with time. Right? Go to back to your equation. Force time graph. Take this across there. Force time graph. Right? Force times time. Force times time is your area under graph. Or in calculus form is integral of F dt. Right? So area under graph is a change in momentum. Area under graph, force times time, change in momentum. Right? So if the body is, assuming the body is moving in a straight line, by how much does the momentum change in 6 seconds? Right? So change in momentum is area under the graph. That area there, 2 times 2. Right? 2 times 2. And the trapezium, right? 2 plus 6 times that one. 6 minus 2 is 4. Divided by 2 times 4. We get 20 Newton second. Right? Next corner. Right? That's the integral we use, change momentum. We can use that, either one. Right? Change the momentum, area under the FD graph. FD graph. Right? Inclined plane, which you must know. Geometry, which you have done in under scalars and vectors, topic 1. There's the normal. Right? It's just a imaginary line perpendicular to the surface. That's 90 degrees. Right? That is your, usually we call the weight of our vertical line. So this is 90 degrees. See, triangle is a right angle triangle, 90 degrees. This is also 90 degrees. This is also 90 degrees. So that angle is 90 minus theta. Right? So this is 90. So this must be theta. Right? So either one, you can call this one theta, memorize it, or derive it. Right? You can either use this angle or can use the angle. Okay, so the inclined plane, that's the object. Consider forces acting on a wooden block. Drawing y and x axis, perpendicular and parallel to plane. Right? The motion is going to be going up or down or perpendicular phase. It's unlikely we'll go downwards there. That's why we choose our axis, x here, y here, perpendicular to the plane. Right? So there's your normal. So there's your y-axis. This is your x-axis. And then we can complete our rectangle to resolve this weight into component parallel to the plane and perpendicular to the plane. Right? So if the weight is 20 Newton and the frictional force is 5 Newton, then replace the weight. Right? If we consider as this angle as 60, angle as 60, then this is a component of weight parallel to the plane. Weight perpendicular to the plane. Parallel to the plane, sorry, is 20 cos 60. It's your 60 here. That's your 20 cos 60. You can use a calculator. And perpendicular plane, this is 1. Right? So it's W, which is 20 sin 60 or cos 30. Right? So 17.3. The resultant falls down the plane. Right? This one is larger than that one there. So subtract. So the resultant force is down the plane, accelerate downwards. 10 minus 5 is 5 Newton down the plane. Going to accelerate downwards. Okay, bench and pulley are smooth. No friction. Calculate the acceleration of the masses. This is your STPM work. Consider the forces acting on both masses separately. You calculate this one. First, that's the one. It has acceleration A. There's a tension pulling it down. So in this case, the only force acting is the tension. Assuming no friction, right? Applying Newton's second law on the 4 kilogram, this one, right? T, which is that, M is for A is acceleration. And look at this one, right? What is acting? There's a 2 kilogram there. Tension is pulling it up. Acceleration is going downwards there. The weight of the ball is pulling it down. So it's going to go downwards. So its W is greater than T minus T equals to 2A. Right? You can put your T into here, or you can add the two together. Right? W equals to 6A. Right? Remember your W in this case is 2G. To calculate A as 9.81 divided by 3. Right? 3.27. Okay. 2 times 9.81 divided by 6. That's why you get 9.81 divided by 3. Okay, let's do a past year paper. Past question. Newton's law of motion. The net force on an object moving in a straight line on a frictionless surface certainly becomes 0. The object will then, right, this is static value, understand Newton's first law. Right? No force acting, it is moving. What's the answer? Right? It cannot stop moving. If it's moving, you continue to move. Require a short time to stop? No, there's no friction there. Slow down gradually, it doesn't slow down because there's no friction. Move with uniform, move with constant velocity. The answer is donkey. Right? The force accelerates the object. When the force goes to 0, the object is moving. Remember, you continue to move with that velocity. Okay, let's try 2016. Number 2, which situation will not happen based on Newton's first law of motion? Force is required to change the state of motion of an object. Right? You want the untrue one, we don't want the true one, correct? To change the state of object, you need a force. When a push is removed from a moving object, the object stops. When you push it, the object is moving. It will continue to move. So force. A push is a force. And the force is removed, the object that's moving continues uniform velocity. An object at rest, the net force acting on the object is 0. True. No resultant force, no net force. When an object moves with constant velocity, the net force acting on the object is equal to 0. True. Right? No acceleration, no net force. The answer is B. Sorry. You want the wrong one. Wrong one is C. Sorry. Okay. And let's try this one. Two forces, 12 Newton, 10 Newton, we act on an object. There's an object there, P, or mass 2 kilogram, are shown in the diagram below. What is the acceleration of P if we move in the direction of OX? Okay, this question is not well said, but we just assume that it's going to move in accelerator OX. So we are going to assume that vertically it's in equilibrium. It's moving along OX. Okay, so the first thing is to find this angle. Right? Draw on the paper the angle theta. For vertical equilibrium, right? Vertical force is 12 sine theta equals to 10. And then you can find your theta. Then you can find the resultant force in the x direction. In the OX direction is 12. Right? Cos of this angle is 6.4, 6.63. Right? That's the resultant force. You want the acceleration, not the force. Right? Don't get caught. They should have given you as part on the answer to catch student. Right? Force divided by mass, which is 3.3. Okay, usually the answer is 2 to 3 significant figure only. Don't need to go too many significant figure. Right? The answer is B. Okay, thank you for your time. See you again next time. We stop the sharing. Thank you.